It's probably good that my whole Felix spiel wasn't in the recording. I was like, come on, get on with it. Yeah, kind of. Yeah, talking about the campus cat. All right, so I left you with a tiny task. All right. All right. So continuing from last day, we were so close to finishing that example. And this is really bugging me. I guess we need some information from before, but all right. I won't make you just jump in. We'll do a little recap of what happened here. Okay, so we had a sample and we had some proportion of defective chips, right? And so then we have a point estimate, right? A point estimate we talked about last day is our best guess at what the population proportion of chips with defects is, right? We just have the sample information, but we really want to know about the whole population, right? And so we talked about our point estimate, and for proportions, we use p hat, right? And so we know that if we took a different sample, right, even if it's randomly selected and things like that, right, then we would get a slightly different p hat, and that's fine, right? We expect variability in our sample proportions. We're only ever going to collect one sample, right? But we know that in theory, if I took another one, it would change a little bit. And if I took another one, it would change a little bit. And so there's spread there, right? And so that spread is the standard error, okay? And just to denote that it's the standard error for p hat, I'm gonna try to use a little subscript p hat, just to denote that that's the standard error of p hat. What's going to happen is we're going to have lots of different standard errors. So that's why it's good to keep track of which one you're talking about, okay? And we've only talked about one so far, right? But it's good to get in that habit. Okay. Oh, hello? Sounds like, no. Let me just go check here. Maybe not. Okay. Just a little slip of the mute, I think. Okay, so then we said, okay, so there's some variability in my p hats, and then so if the historical rate of defects is 10%, right, and we saw 12.74%, right, what we wanted to know is, okay, how does 12.74 compare to 10%? I think as a group, our gut reaction was, oh, that's pretty big, right? But then what we did was we standardized, right? So we calculated the z-score, and we saw that, okay, given the spread, right, 12.74 is really only, let's say, 1.2 standard errors away from 10%. Okay? And this is the first time that we introduced it, but as a rule, right, any value that's more than 2 standard errors from another value, right, that would be considered extreme. Okay, just as a rough guideline. Okay? So 1.2, not a huge deal. It's within that kind of main cluster of information. Okay? All right, so then I left you with this one. Suppose the true population value is found to be 10%. Okay, if we use that proportion, that p, right? So we're told that this is p, 10%. Okay, and we're going to use that instead of p hat. Does the standard error change that much, right? Because remember, we said, okay, well, technically the standard error should be using p, but if I know the population proportion, can't I just look at the entire population, right? How would I have that information, right? And so here, let's see here, use a different color. This is saying that P is 0.10, right? And so, which it says here too. What I'm gonna do is I'm gonna grab this standard error calculation that we already found. Copy. Paste. Okay. And let's see here. Versus the standard error of P hat. Forgot the equal sign. PQ over N. That looks weird. I think because I'm standing up. But I want to see you guys. I'll sit down eventually. And then I'll pop back up. All right. So it's just asking us to just compare is there a huge difference in the standard error if I were to use the value that I'm supposed to use, right? P. We used our best guess, right? Because we don't know P, but what do we get? We get the square root of 0.1 times 0.9 divided by 212. Let's see here, I've got roughly 0.02060408459. To 4 decimal places, 0.0206. Okay. They're both 0.02, right? I'm okay with that. Proportions, so these are proportions, right? It's the spread in the proportions. So it's a spread of what? 2.29% or 2.06%, right? I think those are pretty similar, right? And so here, right? Therefore, using P equal to 0.10 instead of, that doesn't sound like a college kid. Or maybe it is. I think it might be Oliver. Oh, you know Oliver. The campus kid. Yeah. No, Oliver's dad, Sean, works in our office, but yeah. Anyways, he's got an office up here temporarily. The campus kid. So instead of using 0.12, what was it? 74? I'm gonna say it does not change the standard error drastically. All right. 2.29% versus 2.06%. I'm changing them to percentages on purpose because I want to make that link that proportions are communicated in percentages, right? And sometimes it's a little bit easier for our brains, for some reason, when I say 2.29 versus 2.06%, then our brains go, oh, okay, sure, fine, whatever. Whereas here, right, maybe we can get a little bit bogged down, right? And so I'm doing that on purpose just to get you to link those two together. Okay, nice. So let's see here. It's not really review, but that's the end of that. Whatever that was. The end of an era. No. Gonna start it on a fresh page here. Today we're gonna start section 5.2, okay, which builds on what we were talking about earlier. It's really just an extension of what we said earlier, and it is where we introduce confidence intervals. Yeah. like my favorite thing to do all term, because now we did all the work to get to this point where, okay, now we get to do some real stats, okay? And confidence intervals, because what you've been doing, I don't know what you've been doing, but no, it was stats, just different stats. Right, but this is the fun stuff, okay? So confidence intervals, we never call them confidence intervals, but we use them quite often, right? So just in regular speech, we say, you ask me, oh, how many stats courses have you taught? Off the top of my head, I don't know exactly, right? Last time I counted, it was 17, but that was like 3 years ago. So my best guess, my point estimate is 25. I don't know, right? That's my best guess. Then what am I gonna do? I'm not just gonna say 25. I'm gonna say, give or take 3, right? Perfect. That's a confidence interval. Okay, so we take my best guess, your point estimate, and then we build what I like to call just a little buffer, right? Plus or minus, I don't know, 3, 4, right? If I say 3, then what's your follow-up question? Not necessarily, but well, or how confident are you? 90%, right? What would I have to do to increase that confidence? I'd have to increase my buffer, right? 25 plus or minus 5. 25 plus or minus 10, then I should be really confident, right? And so we have this idea of a confidence interval kind of built in. Yes.
But wouldn't the larger your confidence interval
So I am building up to it, but there totally is a trade-off between confidence and precision, right? All of a sudden, I could say 25 plus or minus 25, and I would be very confident, right? But you would be like, try again, Emily. That doesn't help me at all, right? And so there is this trade-off of, right, confidence versus precision. Okay? So as an industry, what we've landed on is 95% is a good kind of trade-off, right? Where we get precise enough results, right? And 95% is confident enough, right? Yes.
So you're saying 95% confidence and 5% precision?
No, it's just a 95% confidence interval. Gives us enough precision, but also a high enough confidence. So there's no easy way to measure precision that we're going to talk about, so that's why I'm avoiding it. You can, but right, it would have to do with the spread. But I had a student ask me a long time ago, and they go, why don't we just make 100% confidence intervals, right? Then we've got that, okay, well, then my bounds would have to go to infinity, right? And then I lose that precision. It's a good idea, but it just doesn't work. So how do we translate that into proportions, right? So what we said last day was, okay, maybe I should write it out first. P hat follows a normal distribution with a mean of P, and I'm going to write P hat, and a standard error of the square root of P hat Q hat over N. Translating this, right, I can draw it. One of my sloppier normal distributions, oh well. Okay, so the normal distribution, so it follows a normal distribution and it's centered on p hat. And the standard error of p hat is the standard deviation, right, of p hat. And it's going to be the square root of p hat q hat over n. That doesn't look like a hat. It's too tiny. There. So that's what that's saying. So any p hat that I draw from a sample, so if I generate a new sample, right, I randomly select a new sample, then those p hats are going to follow this distribution. Okay, so what we want to do is, like I said, I'm just accept it as fact that we're going to build a 95% confidence interval. What that means is you're going to capture the central 95% of the curve, right? So here, 95% of the curve. So what values here and here make that happen? We've already done that. It's almost like we were working up towards this. Almost, right? Okay, so I'll write a little blurb, right? Because instead of using just the point estimate p hat, right, what we're going to do is we're going to build some buffer around p hat, right? P hat, bless you, plus or minus some values, right? So there's going to be a lower bound and an upper bound. Okay, so let me just jot that down. Instead of reporting a single value, the point estimate, we take the spread of the point estimate which is the standard error of p hat, or maybe I shouldn't specify p hat, just the standard error. Because like I said before, all these concepts are also going to transfer to different point estimates, right? So it won't always be p hat, right? But for now it is. Okay. So we take the spread of the point estimate into account and build an interval of plausible values for p. Or maybe I'll say for the parameter. So what we want to do is to build a, let me change color here. To build a 95% confidence interval, which I'm just going to start abbreviating CI here, confidential informant. No, confidence interval. I watch a lot of crime shows. Oh yeah, the CI. So to build a 95% confidence interval, okay, what we're going to do is we're going to move out some number of standard errors from our point estimate. Okay, and you might remember the 68, 95, 99.7 rule, right? Central 68%, 95%. So we're going to move out roughly 2 standard errors away. So that still applies. We're going to have a slightly more precise value, okay? but in general, that's how it's going to work. Okay? So to build a 95% confidence interval, we need to find the upper and lower bounds that capture, and I'm going to use that word a lot. Maybe I shouldn't highlight it yet. I'll highlight it later. That capture the central 95% of the distribution. Around p hat. So visually, right, it looks like this. Okay. Mathematically, what are we doing? We're going to take, okay, we have p hat, and then we want to go down a little, up a little, right? So I'm going to use plus minus. How did I want to do it? Let's say 2, just for a rough approximation. Like I said, we're going to refine that a little bit. Okay. 2 times the standard error of p hat. Right. I want to move down 2 standard errors and up 2 standard errors. Okay. So this value here, we can generalize this value as Z star. Okay. We're going to call that a critical value. Okay. And the critical value is what allows us to change the confidence level. Z star, the critical value. The critical value is what allows us to change the confidence level. Right, 95% confidence interval, 90% confidence interval. Are the most common, but there's lots of other ones that we could do. Okay. All right. So here we have our point estimate. Then we have, oops, the critical value. And then we have the standard error of the point estimate. Oops. Okay. That's going to be the general setup for any confidence interval, right? I have my best guess, and then I build a buffer and I use the critical value to determine the width that I want, right? And then the standard error is the spread. And so then I just need to know what the spread is, and then I can move down to up to standard errors, for example. Okay. All right, so to find the critical value, we're going to use that table that I gave you. Okay. And I've got a little cheater one here. Copy. There it is, huh? Oh boy. So here, now, I think I just kind of squiggled over everything before. We're slowly going to build out this table and start, okay, yeah, okay, there it is. More than that? Good. So here you have your confidence level. We are still going to just ignore everything in between here, but we are going to look at these guys and the Z stars, which, pardon? Yeah. So this midsection is for the T distribution, which is for means. So once we start talking about numerical data, then we're going to be, we're going to have degrees of freedom, and but everything else behaves the same, right? It's just the line that we use changes. So it's a nice transition. All right. So just to clear some things up here, I am only going to ask you for these confidence intervals on a quiz, right? I'm not going to ask you for anything 97%. You go, oh, I know, oh boy, what am I supposed to do here? That's not going to happen, okay? You can use software to find these values, right? So, but in general, I just stick to these guys here. But that's more assignment stuff if you have to find the Z-score value. Yeah. All right, because you should use software. So if we go back to our 95%, which is our default, I'll always tell you what confidence interval or what confidence level I want, right? And that's a dead giveaway that you have to do a confidence interval. Calculate a 90% confidence interval. Okay, got it. In real life, if you're having to choose a confidence level, then just go with 95%. Unless there's some industry standard reason why you would use a wider interval. So medical testing, they want to be really confident. So that's fair, right? So then you would be using one of these kind of larger confidence levels. But just for business or anything like that, you're going to be doing 95. Yeah. If you have really crappy data, you could do a 90% confidence interval. Yeah, just do 95. Yeah. Okay, so in class, so just to write out what I just said, I will always tell you what confidence level to use. Oops, confidence level to use in real life. 95% is the default. Right, and like I said, there are some circumstances where you might want to change that, but in general, 95 is safe. Yeah. Okay. Oh, okay.
Let's go back. So we take a population and then we take a sample from the population. Describe how the population is behaving. Right?
Yes.
Population or p-hat.
Yes.
And how is it linked to the confidence level? How confident we are the sample is behaving, or?
So the problem becomes we only have this one sample that we've collected, right? And so, but the theoretical side says, okay, well, I could have, this is just one of an infinite number of possible samples, or a huge number of possible samples I could have collected, right? And so what we do is we build this confidence interval to try to get a range of possible values for the population proportion, instead of just, oh, I'm pretty confident it's 0.1274, right? Instead, you would say, oh, okay, well, I'm 95% confident that the population proportion is somewhere within these two bounds. Okay, and so, and there are a lot of things that I kind of gloss over and then I go over it again. And so, because there's a lot. Okay? So we'll see. I'll probably fill in the cracks as we go, but
Because we took, let's say, X sample,
mhm,
we did not collect other possible samples. So rather than cross-validating, repeating the sample over and over again, we determined a range of values. So this the value, ranges from this to this. So I am this much confident that this value is going to range from this value to this value. That's why we're doing
okay. So what happens is your population proportion is fixed, right? It exists. In theory, you could collect the entire population of US adults, for example, or all the chips that they produce that week. In theory, you don't want to, you don't have to. So the population proportion here is fixed. It is some number. We don't know what it is. We'll never know what it is. But what we do is, okay, now I take some sample proportion, right? It's my best guess, but I don't know. So here it is. It landed here, right? I don't know. It's close. Depends on the spread, right? So here I am. Here's my, you guys see this? Okay, so here's my population proportion. Here's my sample proportion. There's a number line running along here. Okay, so then what I do is, okay, well, that's not that close, right? Maybe it is, maybe it isn't, right? So then what I do is I take the spread that I calculated using the sample proportion, and then I build out these buffers, right? And so now I don't know where the population proportion is, but now I have this net, right? Where, okay, I'm 95% confident that I've captured it. In this case, I did, right? What if my sample proportion was over here, right? Again, I'm 95% confident I caught it. I didn't, but I don't know that. That's why I'm only 95% confident, right? So now here, yes, got it. I didn't know that, right? But I'm 95% confident, right? And so you don't know where your sample proportion is relative to the population proportion, but that's why you're only 95% confident, right? And so I consider it my job in this course to really make you unsure of yourself, right? A statistician will never commit to anything, right? It's, I'm 95% confident. I could be wrong, right? And so there's always a chance that we're wrong, right? So the probability is never 0, the probability is never 1, that kind of thing. We just skirt around all those absolute statements. Say, okay, I'm 95% confident that it's somewhere in this range, okay? So today I want to teach you how to calculate that range.
So this happens in typical files, right? So
Yeah.
since we take a population and let's say X number of populations, keep them drops and simplify.
Yeah.
And then we try to estimate if that drug is working. So we're 95%.
Yeah. Yeah.
Rest
Yeah, because all you have is your sample information. So it depends on how good your sample was. You did all the work and you did your best at having a good sample, but sometimes you just have these rogue samples, right? And there's no avoiding it. There's no knowing when it's happened. So that's why you can never be sure. Okay. Good. What was I gonna say? Oh yeah. So if I want to move out and capture the central 95% of the curve, right? One thing we could use the empirical rule, the 68, 95, 99, oops, 9.9, no, 99 0.7% rule. Okay. And say that to capture the central 95% of the curve, I would need to move out 2 standard errors, right? And say that to capture the central 95% of the curve, we would move out. I'll put move out in quotes, right? Subtract a little, add a little, move out. We would move out 2 standard errors from p hat. Okay. Using the t-table though, you can call it table C. I call it the t-table often. Okay, I'll know what you mean because you only have one table. So, because I only gave you one, right? So using the table, we see that, okay, to capture the central 95%, what it says is move out 1.96 standard errors. Is 1.96 pretty close to 2? Yes, right? And so that's why the 68, 95, 99.7 rule, it's just a quick kind of guesstimate, right? But if you want to have more precise values without using software, so it's like a continuum, we're going to use 1.96. Okay. And so from the table, we find a more precise value of 1.960 standard errors from p hat. But I do want you to just notice this is close. I'll even say very close to 2. From here on out though, I want you to use the table, right? Be as precise as you can be. Right? And usually I like to mix it up and ask for a 90% or something like that.
That's a Z star, right?
Yeah, so Z star here.
We have been using that Z star to calculate the square in our previous lectures.
Yes, yeah.
For that Z and this Z star.
No.
Because we
But
using this value.
I know. So now we're just using it in a different way. Yeah, because now it's just, we're gonna use it to say, okay, in order to capture the central 95%, I need to move out 1.96 standard errors, right? Whereas before, we used it more for the areas in the tails, right? So we can still do that, but for confidence intervals, we're gonna be using the Z star as that critical value. You know? Okay, good. So let's see here, because I've got some stuff that we're not using the same table. Okay. So where we landed is that in general, a confidence interval has this setup. Okay. A confidence interval and I'll say even any confidence interval has the following setup. Your point estimate, okay, plus minus some critical value times the standard error of the point estimate. So very, very generally. Okay. Now, I'm not going to do this, but what I could do for each section is I could just tell you what the point estimate is and what the standard error of the point estimate is and what the critical value, what distribution it follows, right? And then you can just build a confidence interval. Right? We're not quite there yet, but that's where we're going to get to, okay? And so we're going to work through this, of course, but what I want you to be able to do is leave this course. And even if you come across a point estimate or some sort of parameter that you're not familiar with, right, then you know, okay, all I need is the point estimate and all I need is the standard error of the point estimate. And I can build a confidence interval for this thing, right? It's not new to me. I can do it. Right? And so that's where we want to get to. We're going to cover a lot of the usual suspects. Yeah. But so for p hat, or for the population proportion, we have p hat plus minus some z star times the standard error of p hat. This is going to give us an interval. So I'm going to be really picky about your interval notation because it's important. We use round brackets. Okay, round brackets, and you've got your p hat minus your z star times the standard error of p hat, separated by a comma. So that's your lower value, right? And then your p hat plus your critical value, right? Now move up a little bit times the standard error of p hat, and then end it with a curved bracket. This has to be the lower value. And I'm a real stickler for this stuff because an interval from 3 to 0 doesn't exist, right? 0 to 3 exists, right? So you want to make sure that you're writing them from lower to upper. And I think the reason that people mix them up is not because they don't know what a smaller value is and what a larger value is. You're caught up in, okay, plus minus, so you do the plus one first and then the minus one. And then you jot them down in the wrong order. But you just want to check in and make sure that the interval is true. Okay. So on your formula sheet, maybe it's time for the formula sheet. Where is it? That's old. Here. All right. Whoa, Emily, come on. We're going to work through it though. Just today, we're just going to focus here on this upper part. So I'm only going to grab this stuff. We're going to get there. Oh, what? I don't know what that was. Long time ago. Okay. So here, I tell you the sampling distribution of p hat, right? It follows a normal distribution centered on p with a spread of the square root of pq over n, right? And then the confidence interval for p, right? I'm trying to capture the population proportion p is p hat plus minus z star and then times the standard error of p hat, which is the square root of p hat q hat over n. Okay. Just a couple of notes. This is the standard error of p hat, but also this whole plus minus chunk is called the margin of error, which I'm guessing that you have seen or heard of at some point, especially if you've read kind of journals or stuff like that. Dear diary, no, not like that. like scientific journals, then we usually report the margin of error. So the margin of error is the critical value times the standard error. So I want you to be careful because there are some questions on the assignment that I'll post where it gives you the margin of error, but a lot of people misread it and think it's the standard error. What am I doing wrong? Well, they gave you more than you wanted, I guess. Okay. So, good. I feel like there was something. Okay. We haven't built a confidence interval yet, so we're getting there. But kind of the last housekeeping thing that I want to introduce before we do is how do we interpret a confidence interval? And I'm going to give you a canned answer that I want you to use until it makes sense to you. Okay. And so unlike a lot of, I guess, teachers, I want to give you the right one. I want you to use the right interpretation, and then eventually it will click. Okay. But there's so many ways that you could misinterpret the confidence interval. And so that's why I just want to set you on the right path, memorize it. I don't know, write it on sticky notes all around your house. And then you come in oh yeah, okay, here we go. Read it. Okay, got it. That's what I used to do. Just have sticky notes of things I wanted to remember. I open the cupboard. I'm like, okay, right. Yeah, got it. Have to read it. Anyways, I guess luckily I don't do that anymore. There's nothing I need to memorize anymore. All right. So, but when I do, I know how to do it. Okay. So we need to be able to interpret our confidence interval. We need to be able to interpret a confidence interval. Okay. I'll even say, I want you to use the following format. I tend to use the royal we. We are blank % confident. That's a good start. We are blank %, and this is where you would insert your confidence level. Right? Whatever is appropriate for what you built. 95%, whatever. We are blank % confident that the interval from blank to blank, this is where you put your lower bound to the upper bound of the interval. Captures, and this is where I'm going to highlight captures. The true parameter, the true blank, and this is where you're going to enter your parameter. The parameter, right? We talked about the proportion of US adults who would vote in favor of a candidate, right? And so this blank, this last blank is often quite long, but you just steal the question and reword it as an answer, right? Calculate a 95% confidence interval for the proportion, the true proportion of chips with defects that week, right? we are 95% confident that the interval from blank to blank captures the true proportion of chips with defects produced that week. All right, so you just take the question, reword it as an answer, and sometimes the wording gets a little bit weird, but that's okay. I don't need you to finesse it or anything. You can just take it, turn it into an answer, and I'm fine with that. Okay, it's gonna sound weird sometimes, but I try to make it good on quizzes and stuff. I'm just thinking about assignments. Okay. All right. This is where I have, but we kind of did it. I did the active version of this, right? So when I had the population proportion here, right? What's that? That is this dotted line here. Then I had my sample proportion, which are all the dots. Right? And then you don't know if you have this sample or this sample or this sample or this sample, right? These are all just, this is 25 different samples that they generated, right? And so that's why you're only 95% confident. I'm not going to grab that. It's in your textbook though, so I just wanted to show you. Yeah. All right. I've got an example for us. Back to the textbook. I just closed it. Oh yeah, so here, I'm not going to bring this in because we already talked about it. But it's there if you want to refer to it. But I want, oh, it's not example, it's exercise 513. So we're ready to do our first example. A website is trying to increase registration for first-time visitors, exposing 1% of these visitors to a new site design. Of 752 randomly sampled visitors over a month who saw the new design, 64 registered. Okay. Check any conditions required for constructing a confidence interval. We haven't talked about conditions because we know them all already. They are the conditions for using the normal distribution, right? And so you have to have independence, which if it was randomly sampled, then you can assume independence, okay? And the success failure condition, right? I didn't review those. I forgot to review them, but I said them now. So here we go. So the conditions same as the conditions for using the normal distribution. Right? Because what's one thing we're relying on? That it follows a normal distribution centered on p hat and a standard error of the square root of p hat q hat over n. Right? We need that. If that's not true, we're hooped. So the first condition is independence. It says that it was randomly sampled visitors. So visitors were randomly sampled, right? And so we can assume independence. Even if it didn't say, right, we would have to say, I assume that these visitors were randomly sampled so that we can assume independence, right? So either way, it's all the same. Okay, so visitors were randomly sampled. the second condition is the success failure condition, right? We need to have a sample that's large enough. Okay. Let's jot down. So N is 752 and X is the number of successes, which is 64. Oh. We're ignoring the 1%. That would be if we were checking the less than 10% rule, all right? Then if it's only 1%, it is less than 10% of the population, so then it's satisfied. But like I said, we're ignoring it as I talk about it. So X is 64, which is greater than or equal to 10. I like to do a little check mark. Checks out. Right, which is the observed successes. And for the failure side, observed failures is N minus X, which is 752 minus 64, which is 688, which is also greater than or equal to 10. I used X equal to 64 because I had the number of successes in the question, right? So then I'm just gonna use that. What's another thing you could have done? You could have said, or N times P hat, right? 752 times P hat, but that would require you to find P hat. What's P hat? X over N. So then you have N times X over N. And so that's why these guys just cancel, right? So if you have X, it's just easier. But it's okay if you want to play it safe and you want to just always use N times P hat, that's totally fine, right? But I look for shortcuts whenever I can. Not shortcuts, but yeah, efficiencies. Sometimes so as a student, I definitely would have been doing this just because it's always going to work, right? And then I would kind of get to 64 and be like, oh, right, okay, yeah, whatever. I did it, got it. Okay, so those are the conditions that we need to check, right? There's two conditions that we need to check. Part B, we want to compute the standard error. So B, the standard error of P hat is the square root of P hat Q hat over N, which means I need P hat, finally, right? So first we need P hat, which is X over N. So P hat is 64 over 752. And to 4 decimal places, because that's all I have in my notes here, 0.0851. I don't know if it keeps going or what. But like I said, 4 decimal places as a default is usually pretty good. It's if you have a lot of zeros here, then obviously you need to extend it, right? Get some information, but I'm happy with this. Okay. What does this P hat? This P hat says that the sample proportion of visitors that signed up or whatever it is registered is 8.51%, right? With some spread, right? And that's what we have to find. So then the standard error of P hat is the square root of 0.0851 times 1 minus 0.0851 divided by 752. And we'll bump this down, so just going to show that we had to do that before we could find the standard error. So then the standard error of p hat is roughly 0.010175. Again, to 4 decimal places, 0.0102, mostly because it's annoying to type it all in your calculator. So the standard error is 1.02%. Right? So a spread of 1%. Okay. Pretty good. Construct and interpret a 90% confidence interval for the fraction of, and here I just want to note that a fraction is just a proportion, right? 64 over 752. I don't use the term fraction. I like to kind of lead you down the path that I want, right? What proportion of blah, 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 just to point you in, okay, this is a proportion question. Okay, but we can use fraction, that's fine. So construct and interpret, people always forget that part. A 90% confidence interval for the fraction of first-time visitors of the site who would register under the new design. Okay, assuming stable behaviors by new visitors over time. Okay. I'm gonna drop that last bit, yikes. Okay, so we wanna make a 90% confidence interval, which means that, okay, let's start by jotting down that I need a 90% confidence interval. From the formula sheet, scroll back up there, here, right? If I need a confidence interval for a 1 sample proportion question, right? Trying to capture P, the population proportion, I'm going to use P hat plus minus Z star times the square root of P hat Q hat over N. Okay. So first thing I'm going to do is start out by writing out the equation that I'm about to use. Okay. This is a way to secure part marks as well on the quiz or on the final exam. Because if you tell me what you were going to do and that makes sense, right, then if you followed through or if you have a typo or whatever, then I can at least give you part marks for being on the right track. Or on the flip side, if you picked the wrong formula but you followed through, right, then I can also give you part marks, right? So it's always just safe. Z star times the square root of P hat Q hat over N. We know P hat is 0.0851, and we know the square root of P hat Q hat over N is 0.0102. Okay. And so all we need is Z star. Now from the table, bring it in here. Need Z star for a 90% confidence interval. So here I am at 90, and I just like to go kind of trace my way down. My Z star is 1.645. Notice that all these, right, as we get lower and lower down, they're all pretty well similar, 1.664, 1.660, 1.646. So you want to make sure that you're actually on the Z star line. Yeah.
Sorry, you wrote confidence interval, but we confidence levels, and you said confidence level.
get jiggy with it. Yeah, yeah. Well, so here, so we need the Z star, so we need the critical value for a 90% confidence interval.
Okay.
So the confidence level is 90%, but it's for a 90% confidence interval. Yeah, these are things that I forget. They are totally confusing in the beginning, but we're gonna see a lot of kind of these. Yeah,
A kind of interchange.
yes. The confidence level is just the 90,
Yeah.
right? And then, but we're doing a 90% confidence interval, but of course they have to match. Right. Very tricky. So then here, Z star that we're going to use is 1.645. And again, if you're showing your work properly and you tell me that I'm going to use a Z star of 1.645, or maybe your eyes slipped and you went to 1.282, right? That can happen. That happens, right? Then if you tell me that that's what you're going to use, I'll have to take away a mark, or I usually do half a mark for typos like that. And then, but if you followed through, then you're good. If by some miracle you end up at the right answer, then that's weird, right? And so, and then I get mad sometimes. Okay. Oh, I don't get mad, just sad. All right. So now we have all the components that we need. All right. Now it's just a plug and chug situation, which is kind of a fun math party idea. You're welcome to use it. Have I told you guys I used to have math parties in undergrad, but mostly grad school? I had all these math parties. We used to have derivative offs, where you open Stewart's the classic calculus textbook. You just hit it, and then everyone, so someone calls out the derivative, and then you have to do it, and it's timed. Anyways, it's pretty fun.
Sometimes I do that too.
Cute. Ours was probably a little bit more chaotic. Yeah. I don't know if you guys have taken calculus, but there's a video where a friend of mine, she's super competitive, and she's done. And then but then the moderator, she's like super quiet, super gentle. She looks and she's like, "You forgot the chain rule," which is like pretty basic stuff. And she's like, "Where?" And she goes, "Everywhere." So anyways, yeah, pretty embarrassing, but also pretty funny. Hey, I was plugging in the values. Now I'm just blabbing. Okay, 0.0851. It was a plug and chug that got me. All right, 1.645 times this. Oh, but I already have solved it, which I'm definitely going to take advantage of. I'm not going to calculate it twice. All right, 0.0102. I'm just going to plug that in. And I do that often, especially in a quiz situation, right? Guide you through it, and you're definitely allowed to use values that you've already calculated, right? So like this. Whee! Okay. So then, just stealing from my notes here, 0.0851 plus minus, if I multiply those out, 0.016779. As a note, this value here is the margin of error. Oops. Margin of error is 1.68% if you want to talk about it in terms of percentages. right? Which we often do. Proportions, the 3 Ps, they're all the same, right? Proportions are percentages, are probabilities. In this case, the probability aspect doesn't really apply. It does, but not for us. So 8.51% plus minus 1.68%, right? Seems reasonable. That's a question. No. I used to be so scared to stretch in class. So I had this one teacher who would just attack me. Oh, Emily, you have a question. I'm like, no, I didn't. I didn't. Yeah, so sometimes I'm like, anyways. All right. Once I calculate, so I take away 1.67 or 0.016779 from 0.085, and I get 0.068321. Yeah, so you have to take away first for the lower bound because it's an interval, right? And so, oh, yeah, it is. Thank you. I mean, the margin of error is, you know what? I'm just going to leave it as that. The value is this, but we add and subtract the margin of error. Yeah. Although it's flexible.
It's implicit.
Yeah. So sometimes if I said plus minus 1.68%, right, then you know that, okay, that's the margin of error,
Yeah.
right? But the value itself is the margin of error.
The whole idea of margin of error is that you have this value and you're going above.
Yeah, so that's your buffer part.
Yeah.
Right? You're just moving out a little, move out on either side. And so if we add the two, I get to 0.101879. Okay, so make sure you're using round brackets, separate by commas or 1 comma. Okay. This is your lower bound of the interval, and this is your upper bound of the interval. Or as percentages, we could say 6.83% up to 10.19%. 2 decimal places each. Okay. If you wanted to. All right. Last thing we have to do is interpret this thing. So now interpretation. So what I want you to do is just write out that empty shell, and then we're going to fill it in. Okay. So I use the royal we are blank. And in this case, 90% confident that the interval from blank to blank, right? And the question, so if I go back to how the question is worded, because I'm going to steal that wording, right, is in terms of the fraction or the proportion. And so I'm going to write the interval in terms of the fraction or proportion. If you use the percentage, that's fine, but it should be in terms of the proportion. So from 0.0683 to 0.1019, do some reckless rounding here, captures the true And I use the word true to emphasize that it's the proportion or the population rather. Okay. So the population or the true, and this is where I'm just going to steal from the question and reword it as an answer. The true proportion of first-time visitors of the site who would register under the new design, I'll call it there. Fraction or proportion of first-time visitors. So although it's tedious, it's not hard, right? Because you're just rewording it as an answer. First-time visitors of the site who would register under the new design. End quote. You don't have to have quotes, but and that's just from there. Okay. If you have any questions, let me know. Otherwise, I'll see you tomorrow for hypothesis testing. Ah. And the crowd goes wild.